The first image came through at 3:47 a.m. Eastern Time, December 2022. Jane Rigby, the Webb Operations Project scientist at Goddard Space Flight Center, was on her fourth cup of coffee when the NIRCam data populated her screen. She stared at it for 11 seconds without blinking. "Run the calibration again," she said to no one in particular. The room had 3 other people in it. None of them moved. What Webb had captured wasn't supposed to be there. Not a galaxy, not a cluster. A structure, coherent, threaded, spanning distances that made the Milky Way look like a grain of sand on a beach. The initial measurement put it at over 10 billion light-years across. "That's not possible," someone said behind her. The problem wasn't the size alone. Structures that large take time to form time the universe hasn't had. According to every model of cosmic evolution, nothing this organized should exist in the epoch Webb was observing. The cosmic web has filaments, yes. Superclusters, sure. But this was different. Denser, more defined. Like someone had drawn a line across the universe with a ruler. Rigby pulled up the redshift data. Then she pulled it up again. If you want to understand what Webb found and why it breaks cosmology in a way we can't ignore anymore, hit subscribe. We're going to need the next 18 minutes. Take a breath. Jane Rigby doesn't do drama. 18 years at NASA Goddard. Lead on some of the most technically vicious calibration problems Webb has ever thrown at a human being. And she's developed a reputation for flatline composure. The kind of scientist who finds a mirror actuator failure at T-6 hours and says, "Okay," like someone just told her the coffee's ready. But at 3:47 a.m. on the 18th of December 2022, she said nothing for 11 seconds. The NIRCam feed was live. Primary mirror segments aligned. NIRIS running nominal. They were deep into a survey field designated Goods North, a patch of sky the size of a grain of sand held at arm's length, which is astronomer speak for tiny but ancient. The target was high redshift galaxies, early universe stuff, Webb's bread and butter. Rigby expected galaxies. She got architecture. The screen showed a structure, not a galaxy. Not a cluster of galaxies doing the normal cluster thing where gravity pulls them into a vaguely lumpy cloud over billions of years. This was threaded. Filaments. Coherent curves spanning the entire field of view. And the field of view was already absurdly large. Webb's NIRCam can capture an area roughly the size of a volleyball court if that court were floating 13 billion light-years away. "Run the calibration again," Rigby said. Michael McElwain, the observatory project scientist sitting 3 feet to her left, had already started typing. No one asked if she was serious. When Rigby asks for a calibration check at 3 a.m., you run the calibration check. The room had 4 people in it. The Space Telescope Science Institute's Deep Space Imaging Lab is not built for crowds. Cinder block walls. LED panels that make everyone look slightly dead. A wall of monitors showing live telemetry from a telescope that cost $10 billion and sits 1 million miles away at Lagrange Point 2, which is the gravitational sweet spot where Earth and the Sun's pull balance out and you can park a telescope without burning fuel every 6 seconds. Webb had been fully operational for 7 months. The images it returned were already rewriting intro astronomy textbooks, galaxies that formed 300 million years after the Big Bang, exoplanet atmospheres with sulfur dioxide signatures, star birth in resolutions that made Hubble look like a disposable camera. But this was different. The calibration came back clean. "Okay," McElwain said. "Data's good." Rigby leaned closer to the monitor. NIRCam shoots in infrared wavelengths, invisible to human eyes, but perfect for catching light that's been stretched by 13 billion years of cosmic expansion. What looks red to Webb was emitted as ultraviolet by objects so distant their light has been traveling toward us since before Earth existed, before the Sun existed, before most of the atoms in your body existed. The structure on her screen wasn't one object. It was dozens, maybe hundreds. Galaxies threaded along filaments like beads on a wire. The filaments themselves glowed faintly gas, probably hydrogen ionized by the radiation from young galaxies. But the organization, the curves didn't look random, they looked connected, purposeful. She pulled up the coordinate overlay. The structure spanned 11.3 degrees of arc on the sky. That doesn't sound like much until you do the trigonometry at cosmological distances. At the redshift, they were observing preliminary estimate. Z equals 7.3, meaning this light left its source 13 billion years ago. 11.3 degrees translates to roughly 10 billion light-years of physical space. Pull the Planck comparison, Rigby said. Planck is the satellite that mapped the cosmic microwave background, the afterglow of the Big Bang, the most precise baby picture of the universe we've ever taken. If there's a structure 10 billion light-years across, Planck should have seen its imprint. Tiny temperature fluctuations in the CMB, density variations, something. The overlay loaded. Planck's map of that region showed the normal mottled texture. Slight temperature differences, sure, but nothing coherent, nothing organized. No hint of a structure this massive. That's not possible, someone said. Rigby didn't turn around to see who. She opened the redshift analysis tool. Redshift is how we measure cosmic distance. Light from a distant galaxy gets stretched as space itself expands. The more stretched, the farther away, the longer ago the light was emitted. It's forensic astronomy. You're not looking at where the galaxy is. You're looking at where it was, frozen in time like a photograph from an era so distant that the rules might have been different. The initial redshift reading held Z equals 7.3. Some variance across the structure, Z equals 7.1 at one end, Z equals 7.6 at the other, but that's expected. This isn't a flat image. It's a volume of space-time hundreds of millions of light-years deep. Z equals 7.3 corresponds to roughly 770 million years after the Big Bang. Rigby sat back, rubbed her eyes, did the math in her head that every cosmologist does reflexively when they see an early universe structure. How long would this take to form? Galaxy formation starts with dark matter, invisible stuff that doesn't interact with light but has mass, so it clumps under its own gravity. Those clumps attract gas. Gas collapses. Stars ignite. You get a galaxy. The process takes time. Hundreds of millions of years, minimum, for anything substantial. But that's one galaxy. This was a network of galaxies. Filaments. The cosmic web at a scale that shouldn't develop for billions of years. The simulations are clear on this. You need time for gravity to pull matter together over vast distances. Time for dark matter halos to merge. Time for the universe's expansion to slow down enough that structure can fight back and grow. At 770 million years post-Big Bang, the universe is still an infant, hot, dense, expanding fast. Structures this large don't form. They don't have time. Rigby pulled up the lambda CDM model parameters. Lambda cold dark matter, the standard cosmological model, the one that's passed every test for 30 years. She plugged in the numbers. Formation timescale for a filament structure of this size, 2.1 billion years minimum, probably closer to 3 billion. The universe, at the moment this light was emitted, was 770 million years old. She ran the numbers again. Same result. McElwain was staring at the same screen. Do we tell Mather? John Mather, senior project scientist for Webb, Nobel laureate, the guy who helped design the cosmic microwave background experiments that proved the Big Bang in the first place. Yeah, Rigby said. We tell Mather, but first she saved 17 versions of the image, backed them up to 3 separate servers, and sent encrypted copies to her personal email and 2 colleagues in Germany. Not because she thought the data would vanish, because in 6 hours, when word got out, this image was going to start a fight that would make the Hubble tension look like a friendly disagreement about lunch. The Hubble tension, for context, is the current crisis in cosmology. 2 different methods for measuring the universe's expansion rate give 2 different answers, not slightly different. Different enough that one of them is wrong, or the models connecting them are broken, or something fundamental about cosmology is missing. This structure was going to make that problem look quaint, because if this thing is real, and the calibration said it was real, then either our formation models are wrong, or our timeline is wrong, or the universe had a head start we don't understand. Rigby looked at the clock. 4:03 a.m. In 3 hours, the day shift would arrive. Mather would want a briefing. They'd loop in the near-spec team, the MIRI team, probably escalate to the director's office. By noon, someone would leak it to the Arxiv preprint server, and by dinner, Astronomy Twitter would be on fire. But for 16 more minutes, the discovery belonged to 4 people in a basement room in Baltimore, staring at an image that shouldn't exist. "Get the NIRIS confirmation," Rigby said. "I want depth data, because here's the thing about space. It can lie to you. 2 galaxies, 1 billion light years apart, can look connected from Earth, like 2 cars on a highway that appear side by side, but are actually in different lanes, miles apart. It's called a projection effect, astrophotography's oldest trick. If this structure was real, really real, physically connected, not just a visual accident, then the galaxies in those filaments needed to be at the same distance, same redshift, same cosmic time. NIRIS is Webb's spectroscopy tool. It splits light into wavelengths, reads the barcode of elements in a galaxy's starlight. Most importantly, it gives you precise redshift measurements, not estimates, hard numbers. The data would take 40 minutes to process. Rigby stood up, walked to the coffee station, poured a 5th cup she wouldn't drink, came back. "If this holds," McElwain said quietly, "we're going to need a bigger model." Rigby didn't answer. She was already thinking about the email she'd have to send to Jim Peebles, the 85-year-old physicist who won the Nobel in 2019 for his work on structure formation, the man who literally wrote the equations governing how the cosmic web grows. Those equations don't predict this. Not at Z equals 7.3. Not at this scale, not in a universe 770 million years old. The NIRIS data came back at 4:51 a.m. Redshift confirmation, coherent. The galaxies were at the same distance, cosmologically connected. A real structure in real space, not a projection trick. 10.3 billion light years across. Give or take 400 million. Rigby saved the file. Sent the email to Mather with the subject line, "You're going to want to see this before breakfast." Then she opened a blank document and started typing the sentence no scientist wants to write. "Our observations are inconsistent with current structure formation models." She deleted it. Tried again. "We report the detection of a large-scale structure at Z equals 7.3 with no equivalent in simulation." Deleted that too. Finally she wrote, "Something is wrong, either with the data, the models, or the timeline. We need to figure out which one." That made it into the draft. Outside, the sun was coming up over Baltimore. 1 million miles away, Webb continued its slow orbit around nothing, its mirrors colder than space itself, collecting photons that had traveled for 13 billion years just to ruin someone's morning. 10 billion light years is not a number. It's a conceptual failure. Your brain didn't evolve to handle it, neither did mine. We're built for distances we can walk, throw a rock across, maybe drive in a day if we're ambitious. Cosmological scales don't just exceed our intuition, they break it entirely. So let's start smaller. The Milky Way, our galaxy, is about 100,000 light years across. 1 light year is the distance light travels in a year, 5.8 trillion miles. Already we're in brain melt territory, but stay with me. The Milky Way is big, absurdly big. If you could fly a jet across it at 500 miles per hour without stopping, without slowing, the trip would take 120 million years. Now take that galaxy, shrink it to the size of a quarter, a coin you can hold between your fingers. On that scale, the structure Webb found would stretch from New York to Tokyo, then back, then halfway around the Earth again. That's 10 billion light years. But the size alone isn't what makes this a problem. Plenty of things in the universe are incomprehensibly large. The cosmic web, the large-scale structure of the universe, has filaments that span similar distances. Galaxy superclusters, like the Laniakea supercluster, which contains the Milky Way, stretch across 500 million light-years. The Hercules Corona Borealis Great Wall, the largest known structure before Webb's discovery, measures roughly 10 billion light-years. The problem is when. Time is the knife that cuts this open, because structures don't just appear, they form, and formation takes time. Specific, calculable amounts of time based on how gravity works, how fast the universe is expanding, and how dark matter clumps together. Here's the issue. The light Webb captured left those galaxies 13 billion years ago. We're seeing them as they existed 770 million years after the Big Bang. The universe, at that moment, was an infant. Young, hot, still cooling from its explosive birth. And according to every model of cosmic evolution, that infant universe did not have time to build something this organized. Think of it like mold on a shower curtain. You hang a clean curtain. Over weeks, tiny spots appear. Over months, those spots spread. Eventually, if you're a terrible person who never cleans those spots, connect into patterns, networks, a fuzzy map of neglect. But that takes time. If you hung the curtain yesterday and today, it's covered in a coherent web of mold. Something is deeply wrong. Either the curtain came pre-molded, or mold grows faster than biology allows, or you've misunderstood how long the curtain has been hanging. The structure Webb found is the mold that shouldn't be there yet. Let's get technical for a moment, because this is where the cosmology breaks. Structure formation in the universe begins with dark matter. We don't know what dark matter is. It doesn't emit light, doesn't interact with electromagnetic radiation, doesn't show up in any detector we've built, but we know it exists because galaxies move wrong without it. Their outer stars orbit too fast. Clusters of galaxies hold together when they shouldn't. Something invisible is providing extra gravity. Current estimates: dark matter makes up 85% of all matter in the universe. After the Big Bang, dark matter starts clumping under its own gravity. Tiny density fluctuations, quantum blips, inflated to cosmic size during the universe's first fraction of a second, become seeds. Dark matter falls into those seeds. Clumps grow. As they grow, their gravity strengthens. They pull in more dark matter, more gas. Eventually, the gas collapses and ignites into stars. You get galaxies. But here's the timing. This process is slow. Not slow by human standards. Slow by cosmic standards, which means almost incomprehensibly gradual. The first dark matter halos the invisible scaffolding where galaxies will eventually form take about 100 million years to develop. The first stars ignite around 200 million years after the Big Bang. The first galaxies assemble over the next few 100 million years. And that's just individual galaxies. For galaxies to organize into filaments, long, coherent threads of matter spanning billions of light years, you need those galaxies to talk to each other gravitationally. Gravity is fast compared to a human lifetime, but glacial compared to light. Two galaxies, a billion light years apart, can't influence each other quickly. Their gravity pulls at the speed of information in the universe, the speed of light. At cosmological distances, that means billion-year timescales. The lambda CDM model, our current standard cosmological model, runs these calculations with absurd precision. It includes the density of matter, the strength of dark energy, the expansion rate of the universe, the temperature of the cosmic microwave background. Feed it the initial conditions of the universe, let the simulation run, and it spits out predictions for when structures of various sizes should form. According to lambda CDM, a filamentary structure 10 billion light-years across should not exist until the universe is at least 2 billion years old, maybe 3 billion, to be safe. Webb is showing it at 770 million years. That's not a small discrepancy. That's not a rounding error or a calibration offset. That's the difference between a toddler learning to walk and a toddler building a suspension bridge. Jane Rigby knew this the moment the redshift data came back. So did everyone else in that room. The question immediately became, What are we looking at? 3 possibilities, all uncomfortable. First, measurement error. Maybe the redshift is wrong. Maybe the structure isn't as distant as it appears. Maybe there's some gravitational lensing effect, where a massive foreground object bends light from background objects that's creating an illusion of coherence. Rigby's team spent 2 days checking this. They cross-referenced the NIRCam data with NIRISS spectroscopy, pulled archival data from Hubble, which had surveyed the same field years earlier at lower resolution, and ran the redshift calculations 4 separate ways. Every method confirmed the same result. Z equals 7.3. Distance, 13 billion light-years. Age of universe at emission, 770 million years. No measurement error. Second, projection effect. Maybe the structure isn't real. Maybe it's dozens of unrelated galaxies scattered across different distances that just happen to look aligned from our perspective. Like constellations, Orion the Hunter isn't a real object. It's stars at wildly different distances that form a pattern only from Earth's viewpoint. This one takes longer to rule out. You need depth data. Precise redshift measurements for individual galaxies along the filaments. If they're all at the same distance, same cosmic time, then the structure is real. If they're scattered across different redshifts, it's a visual accident. NIRISS provided the answer. The galaxies were at the same distance. Redshift variance, less than 3%. Cosmologically, they're neighbors. The structure is real. Third possibility, the models are wrong. This is the option no one wants. Lambda CDM has passed every test for 3 decades. It predicted the cosmic microwave background's temperature fluctuations before we measured them. It predicted the abundance of light elements in the universe. It predicted the large-scale structure we see in the local universe, the cosmic web, the distribution of galaxies, the voids. But it didn't predict this. If the structure is real, and it is, and if the redshift is correct, and it is, then something about our understanding of structure formation is incomplete. Either dark matter behaves differently in the early universe than we thought, or the initial density fluctuations were larger than the cosmic microwave background suggests, or there's a missing ingredient in the formation process we haven't discovered yet. By December 21st, Rigby's preliminary report hit the internal STSI servers. Subject line, Goods North, large-scale structure at Z equals 7.3, 32 pages, 17 figures, one conclusion that made her rewrite the abstract 6 times. Formation timescale inconsistent with LCDM predictions by factor of 2.6. Translation. According to the model, this structure is 2.6 times too young to exist. Mather read the report in one sitting, sent back a single sentence. Who else has seen this? Just the observation team, Rigby replied. 12 people. Keep it that way until we have independent confirmation. Too late. Someone had already uploaded a preprint to Arxiv. There's a rule in cosmology that nobody talks about at dinner parties, because it sounds either obvious or insane depending on your blood alcohol level. The cosmological principle. It states, the universe, when viewed at sufficiently large scales, is homogeneous and isotropic. Homogeneous means the same everywhere. Isotropic means the same in all directions. It's the assumption that there's nothing special about our location in space. No center, no edge, no privileged viewing angle. Zoom out far enough, and the universe looks like a uniform soup of matter and energy, the same here as it is 10 billion light-years away. This principle isn't just philosophical decoration, it's load-bearing, general relativity. Einstein's theory of gravity, the foundation of modern cosmology, uses it as a starting assumption. The equations that describe the expansion of the universe, the evolution of cosmic structure, the fate of everything, all begin with, assume the universe is roughly the same everywhere, and for a century, that assumption has held. We've mapped the cosmic microwave background, the afterglow of the Big Bang, across the entire sky. It's smooth. Temperature variations, less than 1 part in 100,000. We've surveyed millions of galaxies. They cluster, sure, but the clustering averages out. Look at a cube of space 300 million light-years on a side. Then look at another cube the same size somewhere else in the universe, and statistically, they're identical. Same number of galaxies, same amount of matter, same distribution. The cosmological principle works. Until Webb's structure, because here's what homogeneity and isotropy don't allow. A single coherent structure, 10 billion light-years across. Not at z equals 7.3, not in a universe 770 million years old. That structure is too big, too organized, too early. It violates the statistical smoothness we've come to expect. Let me make this concrete. Imagine you're looking at mold growing on bread, not on one slice on an entire loaf. You expect some slices to have more mold than others. Random variation. Maybe one side of the loaf was closer to moisture. Fine. But what you don't expect is for the mold on 12 different slices to form a single connected pattern, a coherent design that spans the entire loaf as if someone painted it deliberately. That's what Webb found. A pattern where there should only be randomness. The cosmological principle allows for structure. It predicts structure. Gravity pulls matter together. You get galaxies, clusters of galaxies, superclusters. The cosmic web filaments of galaxies, stretching across hundreds of millions of light-years, separated by voids where almost nothing exists. We've known about the cosmic web since the 1980s. It's normal, but there's a scale limit. Beyond a certain size, roughly 1.2 billion light-years, according to theory, structures shouldn't be coherent anymore. The universe's expansion, the random distribution of initial density fluctuations, the finite speed of gravity, all of these conspire to smooth things out. You can have a filament 500 million light-years long, maybe a billion if conditions are right, but 10 billion light-years? Coherent across cosmological time? That's not smoothing out. That's organization at a scale that shouldn't exist. Marcia Ricci saw the preprint on December 22nd. Ricci is the principal investigator for NIRCam, Webb's primary camera, the instrument that captured the structure. She's at the University of Arizona. She's been building space telescopes since 1978. She does not panic easily. She panicked, not publicly. Scientists don't panic publicly. But she sent an email to Rigby at 6:14 a.m. Arizona time with the subject line, "Is this a joke?" Rigby's reply, sent 11 minutes later, "I wish." Ricci called a meeting. STS-SCI, Goddard, Arizona, ESA, Reps, the Webb Project Scientist Office. Zoom call, 15 people. Topic: do we have a cosmological principle violation? Nobody wanted to say yes, but nobody could say no. The problem is this: if the structure is real, and every piece of evidence says it is, then one of three things has to give. Option 1. The cosmological principle is wrong. The universe is not homogeneous at large scales. There are special regions, structures that don't average out. If true, this doesn't just tweak cosmology, it detonates it. General relativity's solutions for an expanding universe assume homogeneity. Remove that assumption and you have to resolve the equations. Maybe the universe expands at different rates in different places. Maybe our measurements of the Hubble constant are wrong because we're in a weird neighborhood. Maybe dark energy isn't constant. The implications spiral out of control fast. Option 2. The structure formed differently than we think. Maybe the initial density fluctuations after the Big Bang were lumpier than the cosmic microwave background suggests. Maybe there's a population of primordial black holes we haven't detected that seeded early structure formation. Maybe dark matter has interactions we don't understand, some kind of self-interaction or coupling to dark energy that accelerates clumping in the early universe. Option 3. We're seeing something that looks like a structure, but isn't. Some kind of observational artifact. A cosmic coincidence. Galaxies at different distances that happen to align. Gravitational lensing creating phantom filaments. A calibration issue we haven't caught yet. The Zoom call spent 4 hours on option 3. Everyone wanted option 3 to be true. It's the safest. It doesn't break physics. It just means Webb fooled us temporarily, and we'll figure it out with more data, but the depth data killed it. NIRIS spectroscopy confirmed. The galaxies are at the same redshift. They're physically associated. The structure is real in three-dimensional space, not a two-dimensional illusion. So option 3 was out. That left option 1 or option 2, both terrifying. Reek, on the call, said what everyone was thinking. If we're wrong about homogeneity, we're wrong about everything downstream from it. Daniel Eisenstein from Harvard, also on the call, pushed back. Eisenstein runs some of the largest galaxy surveys in astronomy. He stared at cosmic structure for 20 years. The CMB is smooth, he said. Planck measured it to absurd precision. Temperature fluctuations 1 part in 100,000. If the early universe had density variations large enough to seed this structure, Planck would have seen them. Unless, Rigby said, the fluctuations are there and Planck's resolution can't resolve them. Silence. Planck's resolution is about 5 arc-minutes, roughly 1/6 the width of the full moon. On cosmological scales, that's not bad, but it's not perfect. If the density fluctuations that seeded Webb's structure were smaller than Planck's resolution localized, sharp peaks in the primordial density field, they'd be invisible to CMB observations. They'd only show up later, after galaxies formed, after structure grew, after Webb pointed at the right patch of sky. That's a hell of an assumption, Eisenstein said. Yeah, Rigby replied. But it's not impossible. Here's the thing about the cosmological principle. It's an approximation. Everyone knows this. Cosmologists aren't idiots. They know the universe isn't perfectly smooth. There are galaxies, clusters, voids, but the principle holds statistically. Average over large enough volumes, and the lumpiness washes out. The question is, what counts as large enough? For decades, the answer has been 300 million light-years. Survey a sphere of space that size, and you get a representative sample of the universe. All spheres that size, anywhere in the cosmos, should look statistically similar. Webb's structure is 10 billion light-years, 30 times larger than the homogeneity scale. If structure exists at that scale, coherent, organized structure, then the homogeneity scale is wrong. The universe doesn't smooth out at 300 million light-years. Maybe it smooths out at 20 billion light-years. Maybe it never smooths out completely. Maybe the cosmological principle is an approximation that works locally but fails universally. And if that's true, then every measurement we've ever made that assumes homogeneity, the Hubble constant, the age of the universe, the density of dark matter, the acceleration due to dark energy, all of those are suspect. Not wrong, necessarily, but derived under false assumptions, like calculating the speed of a car by assuming the road is flat, when actually it's full of hills. By the end of the Zoom call, no one had answers, just a list of follow-up observations and a shared sense that something foundational had cracked. Riki sent a memo to the Webb project office later that day. Subject: request for director's discretionary time. Translation: we need more telescope time immediately, outside the normal proposal process, because this can't wait. The request was approved in 14 hours. Webb would revisit the field in January. Different filters, longer exposures, independent confirmation. But Rigby already knew what they'd find. She checked the archival data. Hubble had imaged that same region in 2004. Lower resolution, yes. Shorter wavelengths, but the structure was there, faint, barely visible, but there, which meant this wasn't a Webb artifact. 2 different telescopes, 2 different instruments, same structure. The universe had built something it wasn't supposed to build, and it had done it in less time than the laws of physics allowed. Someone, somewhere, was going to have to explain how. Redshift is forensic astronomy. You're not measuring where something is, you're measuring when it was. Every photon that hits Webb's mirrors is a time traveler. It left its source some distant galaxy, some ancient star millions or billions of years ago, and it's been flying through expanding space ever since. By the time it reaches us, it's exhausted, stretched, older. The stretching is literal. Space itself expands, and light stretches with it. A photon emitted as ultraviolet leaves its galaxy, crosses billions of light years of expanding universe, and arrives at our telescope as infrared. The wavelength increases. In physics, longer wavelengths mean redder light, hence redshift. The amount of stretching tells you how much the universe has expanded since the photon was emitted. And since we know the expansion rate roughly, frustratingly roughly, but that's another story, we can convert that stretching into a time. A cosmic timestamp. Redshift z equals 0 means no stretching. The object is here, now, today. Redshift z equals 1 means the universe has doubled in size since the light was emitted. That corresponds to about 8 billion years ago. Redshift z equals 7.3. The value Webb measured for this structure means the universe has expanded by a factor of 8.3 since the light left those galaxies. Run the math. Plug it into the lambda CDM model. Account for how the expansion rate has changed over time, faster in the early universe, slower in the middle, accelerating again recently thanks to dark energy. Z equals 7.3, corresponds to 770 million years after the Big Bang. The universe is 13.8 billion years old today. We're looking back 13 billion years. We're seeing these galaxies as they existed when the universe was 5.5% of its current age. If the universe were a human lifetime 80 years, we'd be looking at a photograph from age 4.5. Now imagine that photograph shows the 4-year-old building a suspension bridge. That's the problem. Let's talk about what the universe looks like at different redshifts, because this matters. Cosmology isn't like history, where you can just read backwards through records. We can't visit the early universe, we can only observe it. And the farther back you look, the weirder things get. Z equals 0 to Z equals 0.5, the recent universe. Galaxies look like galaxies. Spirals, ellipticals, the same structures we see nearby. Stars, gas, dust, all behaving normally. This is the cosmological equivalent of looking at last week's photos. Nothing surprising. Z equals 0.5 to Z equals 2, the adolescent universe. Galaxies are messier, more gas, more star formation. You start seeing massive collisions, mergers, galaxies eating each other. The universe is more violent here, more active. Like looking at your hometown 30 years ago when there were more bars and fewer Starbucks. Z equals 2 to Z equals 6, the teenage universe, peak star formation. Galaxies are cranking out stars at rates 10 to 100 times faster than today. Quasars everywhere, supermassive black holes gorging on gas and lighting up like cosmic searchlights. This is the universe's wild phase. Everything is brighter, hotter, denser. Structure exists, but it's chaotic. Filaments are forming, but they're ragged, incomplete. Z equals 6 to Z equals 10, the infant universe. The cosmic dark ages are ending. The first stars have ignited. Hydrogen gas, which filled the universe like fog, is being ionized, ripped apart by ultraviolet radiation from those first stars. This process, called reionization, is messy and uneven. Some regions are ionized, others aren't. The universe is patchy. Galaxies are small, weird, not yet settled into familiar shapes. And structure, large-scale structure, filaments spanning billions of light years, shouldn't exist yet. Shouldn't. Webb's structure sits at Z equals 7.3, right in the middle of that infant epoch. The NIRISS data didn't just give one redshift, it gave hundreds. Each galaxy in the structure got its own measurement. Rigby's team plotted them. The distribution was tight. Z equals 7.1 at one end of the structure, Z equals 7.6 at the other. Variance less than 3%. That tightness is important. It means these galaxies formed at roughly the same time. They're part of the same cosmic generation. They didn't just happen to line up by accident, they're gravitationally bound, part of a single coherent web of dark matter and gas. But here's what makes Z equals 7.3 so devastating? It's early enough that the universe hasn't had time to build this, but late enough that we can see it clearly. Earlier, say, Z equals 10, and the structure might not have fully formed yet. We'd see hints, precursors, density fluctuations that would eventually become filaments. Later, Z equals 5, and no one would be shocked. By that point, the cosmic web is well established. But Z equals 7.3 is the worst possible value. It's the zone where lambda CDM says, not yet, and Webb says, look at this thing. Adam Rees Johns Hopkins, Nobel laureate for discovering the accelerating expansion of the universe, saw the preprint on December 23rd. He didn't work on Webb, wasn't part of the observation team, but he's one of the world's experts on cosmological measurements, and his email inbox was already full of people asking him what the hell was going on. He ran his own timeline calculation. Different code, different assumptions, same lambda CDM framework. His result: to form a structure this size by Z equals 7.3, you'd need initial density fluctuations at least twice as large as what Planck observed in the cosmic microwave background. He sent his calculation to Rigby with a one-line note. Either Planck missed something or gravity worked differently back then. Both options were bad. Planck didn't miss things. The Planck satellite spent 4 years mapping the cosmic microwave background with precision that borders on absurd. Temperature measurements accurate to millionths of a degree, angular resolution down to 5 arc minutes. It mapped the tiny density fluctuations in the infant universe, the seeds that would eventually grow into galaxies and clusters. Those fluctuations were small, 1 part in 100,000. That's the data. That's what the universe looked like 380,000 years after the Big Bang. Lambda CDM takes those fluctuations and runs them forward in time. Gravity amplifies them. Dark matter clumps. Gas follows. Galaxies form. The cosmic web grows. The model predicts with testable accuracy when structures of various sizes should appear, and it predicts that a 10 - billion light-year structure shouldn't exist at Z equals 7.3. So either the initial fluctuations were larger than Planck saw hidden somehow, localized in ways the CMB couldn't detect, or the growth rate was faster than lambda CDM predicts. Faster growth means stronger gravity or more efficient clumping. Maybe dark matter isn't entirely cold. Maybe it has interactions, some kind of self-coupling that accelerates structure formation in dense regions. Maybe there's a fifth force we haven't discovered yet, something that acts only at cosmological scales, only in the early universe. Or maybe, and this is the option that keeps cosmologists awake at night, maybe the universe is older than we think, not older today. The age of the universe today is well constrained, 13.8 billion years, give or take 20 million. We know that from the CMB, from stellar ages, from radioactive decay in meteorites. But what if the early universe aged differently? What if time itself, proper cosmic time, ran faster in the first billion years than our models assume? This sounds like science fiction, but it's not. General relativity allows for time dilation at cosmic scales. If the density of the universe was different than we think in the early epochs, if dark energy behaved differently back then, the expansion history changes. The redshift to time conversion changes. Z equals 7.3 might not correspond to 770 million years. Maybe it corresponds to 1.2 billion years, maybe 1.5 billion. That would give structure more time to form. Problem solved. Except it creates a dozen new problems. If the early universe was older than we think, then the cosmic microwave background data doesn't fit. The abundances of light elements, hydrogen, helium, lithium, produced in the first 3 minutes after the Big Bang, don't fit. Stellar evolution models don't fit. You fixed one problem by breaking everything else. Rigby knew all this. So did Rias. So did everyone staring at the data. On December 27th, an independent team in Geneva ran their own simulation. They used a modified lambda CDM model with enhanced early dark matter clustering an ad hoc tweak, not based on any known physics, just a what-if experiment. They cranked up the clumping efficiency in the first billion years by a factor of 1.8. The simulation produced a structure almost identical to what Webb observed. Same size, same morphology, same redshift. But the parameters they used to make it work violated constraints from the cosmic microwave background by 4.2 sigma. In statistics, 3 sigma is strong evidence, 5 sigma is discovery, 2 sigma is this probably isn't real, but we can't quite dismiss it yet. The Geneva team published their result with a caveat. Our model reproduces the observed structure, but is inconsistent with Planck CMB data. Further investigation required. Translation: we can make the math work, but only by breaking something else. That's where things stood by New Year's. Webb had found a structure. The structure was real, the redshift was confirmed, the timeline didn't work, and every attempt to fix the timeline broke something else in cosmology. Rigby spent New Year's Eve writing the official STSI press release. It went through 11 drafts. The final version, approved by the director's office, said JWST has detected a large-scale structure at redshift 7.3. The formation timescale and morphology are currently unexplained by standard models. Additional observations are scheduled. Careful language. No claims of crisis. No mention of the cosmological principle. Just, we saw something. We don't understand it yet. We're looking into it. The press release went live on the 4th of January 2023. Within 6 hours, it was the top story on Science, Nature News, the New York Times. By evening, JWST structure was trending on Twitter. Astronomy forums exploded. YouTube science channels scrambled to explain what a redshift was. And in Basel, Switzerland, an 85-year-old physicist named Jim Peebles read the paper, stared at figure 3 for a long time, and wrote an email to Rigby. Subject: we need to talk. Jim Peebles doesn't do email well. He's 88 years old. He won the Nobel Prize in 2019 for theoretical discoveries in physical cosmology. He wrote the equations that describe how structure grows in an expanding universe. He's the reason we understand the cosmic web at all. His email to Rigby was 3 sentences. I've looked at your data. The structure shouldn't be there. I need to see the power spectrum. Power spectrum. The term sounds technical because it is. It's a way of quantifying structure in the universe, how much clumping exists at different scales. Small scales, individual galaxies; medium scales, clusters; large scales, filaments and superclusters. Plot the amount of structure versus the size of that structure, and you get a curve. That curve is the power spectrum. The curve has a shape, a specific shape predicted by lambda CDM. It rises, peaks around 300 million light-years, then falls off at larger scales. That peak and that fall-off are not arbitrary. They come directly from the physics of how dark matter clumps, how fast the universe expands, and how much time has passed since the Big Bang. If you measure the power spectrum of the universe today, survey millions of galaxies, calculate their clustering, you get a curve that matches lambda CDM almost perfectly. We've done this. Projects like the Sloan Digital Sky Survey have mapped a quarter of the sky. The match is scary good. Theory predicts the curve to 3 decimal places. Observations confirm it. But that's the universe today, at z equals 0, after 13.8 billion years of structure growth. Rigby knew what Peebles wanted. He wanted the power spectrum at z equals 7.3. He wanted to see how much structure existed in the early universe and compare it to what lambda CDM predicts should exist at that epoch. She ran the calculation. It took 2 days. Not because the math is hard, it's mostly Fourier transforms and statistical binning, but because extracting a clean power spectrum from Webb data requires removing foreground contamination, correcting for the telescope's sensitivity variations, and accounting for the fact that you're not seeing the entire universe, just a narrow slice. The result came back on January 8th. The power spectrum at large scales, structures bigger than 1 billion light-years, was elevated. Not slightly elevated. 3 times higher than lambda CDM predicts for z equals 7.3. 3 times. Rigby stared at the plot, rechecked the code, ran it again with different binning. Same result. She sent the plot to Peebles. No explanation, just the image. His reply came 6 hours later. This is a problem. Understatement. Peebles doesn't do drama either. Let's unpack what this means. In the 1960s, Peebles, then a young postdoc at Princeton, started working on how structure forms in an expanding universe. The Big Bang had been confirmed. The cosmic microwave background had just been discovered, but nobody knew how you got from a smooth, hot early universe to the lumpy, structured universe we see today. Galaxies, clusters, voids. How did that happen? Peebles built the mathematical framework. He started with general relativity, Einstein's equations for how gravity warps space-time. He added the expanding universe. He added small density fluctuations, tiny overdense and underdense regions in the primordial gas. Then he asked, what happens next? Gravity amplifies the overdense regions. More matter means stronger gravity. Stronger gravity pulls in more matter. Positive feedback. The overdense regions grow denser. Eventually they collapse into dark matter halos. Gas falls into those halos. Stars form. Galaxies ignite. But here's the key. The growth rate is limited. Gravity pulls at a finite speed. The universe expands, fighting against collapse. Dark matter is cold, meaning it moves slowly, meaning it clumps efficiently, but not instantaneously. You can write down differential equations that describe this process. Solve them, and you get predictions for when structures of various sizes should appear. Peebles did this in the 1970s and 80s. Others refined it. By the 1990s, the framework was robust enough to make testable predictions. Simulations could run the equations forward in time, starting from the conditions measured in the cosmic microwave background, and output what the universe should look like at any given redshift. One of the most famous simulations is called the Millennium Simulation, ran in 2005. 10 billion particles representing dark matter. Cosmological volume 500 million light-years on a side. Started at z equals 127, just after the CMB was emitted, and evolved forward to z equals 0. The output: a synthetic universe, a cosmic web of filaments, clusters, voids, structures growing, merging, forming galaxies. The Millennium Simulation matched observations of the local universe almost perfectly. Same galaxy counts, same clustering, same filament sizes. Lambda CDM worked. But the Millennium Simulation, and every simulation like it, made a prediction about the early universe too. At z equals 7.3, structure should be small. Galaxies exist, sure. Small groups of galaxies, maybe. Protofilaments starting to form. But nothing coherent at the scale of billions of light years. The universe is too young. Gravity hasn't had time to organize matter across those distances. Webb's power spectrum said otherwise. At large scales, there was 3 times more structure than predicted. Peebles, in his reply to Rigby, attached a PDF, a hand-drawn sketch. He'd calculated what the power spectrum should look like at z equals 7.3 using the standard lambda CDM parameters. He'd overlaid Rigby's observational data. The 2 curves matched at small scales, individual galaxies, small clusters, but at large scales, they diverged. The observed curve went up. The predicted curve went down. In the PDF, Peebles had written in the margin, either the initial conditions are wrong, or the growth rate is wrong, or both. Initial conditions. The state of the universe 380,000 years after the Big Bang, as measured by Planck. The density fluctuations, the seeds of structure. If those were wrong, if Planck missed something, then everything downstream is wrong. Growth rate, how fast structure grows under gravity. This depends on the density of dark matter, the expansion rate, and whether dark matter interacts with itself or anything else. If the growth rate is wrong, then our understanding of dark matter is wrong. Both options rewrite cosmology. Rigby called a meeting. January 12th, STSCI, plus remote participants from Princeton, Cambridge, Caltech, ESA. Peebles dialed in from a hotel room in Vancouver where he was giving a lecture series. 60 people on the call. Topic: what do we do with this? 3 proposals emerged. First, assume the data is correct and modify lambda CDM. Add a new parameter. Maybe dark matter has self-interactions. Maybe there's a fifth force. Maybe early dark energy, a hypothetical energy field that accelerates structure formation in the first billion years, then disappears, is real. Fit the new parameter to Webb's power spectrum. Make predictions. Test them. Second, assume lambda CDM is correct and something's wrong with the measurement. Maybe there's systematic error in the redshift determination. Maybe foreground contamination. Maybe the structure isn't as large as it appears. Go back to the data. Dig deeper. Find the error. Third, wait for more data. Webb was scheduled to observe 2 additional fields in February and March. If those fields show similar large-scale structure at Z equals 7.3, it's a pattern. If they don't, maybe this is a cosmic fluke, a rare overdensity, a statistical outlier, not representative of the universe at large. The meeting spent an hour debating. Peebles finally spoke up. I think we should consider that the initial conditions are not what Planck measured. Silence on the call. Planck measured the CMB at Z equals 1,100. Peebles continued. That's 380,000 years after the Big Bang. We're assuming those fluctuations, 1 part in 100,000, are the only seeds. But what if there are additional fluctuations, smaller scales, below Planck's resolution, or non-Gaussian features, sharp peaks in the density field that don't show up as temperature fluctuations? Planck wouldn't see them, but they'd still seed structure. That's a big assumption, someone said. Yes, Peebles replied, but we're looking at a big structure. Non-Gaussian fluctuations. This is jargon that needs unpacking. When cosmologists say the CMB fluctuations are Gaussian, they mean the distribution of hot and cold spots follows a bell curve. Random, no special patterns. This is what inflation, the rapid expansion in the first fraction of a second after the Big Bang, predicts. Inflation stretches quantum fluctuations to cosmic size, and quantum fluctuations are Gaussian. Random noise, amplified. But if inflation had a glitch, some brief period where the expansion rate changed, or a secondary field kicked in, you could get non-Gaussian features, sharp spikes in density, localized regions where matter clumped faster than elsewhere. These wouldn't look like temperature fluctuations in the CMB because they're small and dense, but they'd grow into structure faster than the Gaussian seeds. This isn't crazy speculation. Several inflation models predict non-Gaussian features. The problem is, we've never detected them. Planck searched, found nothing. The CMB looks perfectly Gaussian to within measurement error, but Planck's resolution is finite. If the non-Gaussian features are smaller than 5 arcminutes, smaller than Planck can resolve, they'd be invisible. Rigby asked the obvious question, how do we test this? Peebles thought for a moment. You look for more structures. If this is a fluke, you won't find others. If non-Gaussian seeds are real, you'll find them everywhere. Webb should see large-scale structure at Z equals 7 to 8 inches, every deep field. And if we don't, then we're back to modifying the growth rate, which means modifying dark matter physics. The call ended without consensus. 3 camps formed. One wanted to publish immediately, get the data out, let the community argue. Another wanted to wait for follow-up observations. The third wanted to bury it until they understood what they were looking at. Rigby, as lead author, had final say. She decided, publish the detection, but frame it carefully. No claims about cosmological crisis. Just report the observation, the redshift, the size, and note that it's unexpected given current structure formation timescales. The paper went to Nature on January 20th, submitted under embargo. Peer review would take weeks, but the preprint was already out. And the internet doesn't wait for peer review. By January 25th, 6 independent theory papers had hit arXiv, all attempting to explain Webb's structure. 3 invoked modified dark matter. 2 invoked early dark energy. 1 proposed a new inflation model with built-in non-Gaussian features. None of them worked cleanly. Each fixed the structure problem, but broke something else. CMB constraints, Big Bang nucleosynthesis, local measurements of the Hubble constant. Peebles, in a follow-up email to Rigby, wrote, "This is what a paradigm shift looks like at the beginning. Nothing fits because the paradigm hasn't shifted yet. We're trying to patch an old framework. Eventually, someone will propose a new framework. That's when things get interesting." He attached a second PDF, another hand-drawn sketch. This one showed the cosmic timeline with 2 annotations. At Z gleich 1100, what Planck tells us. At Z equals 7.3. What Webb tells us. Between them, he'd drawn a question mark. Underneath, in his handwriting, something happened here that we don't understand. By February 2023, the cosmology community had split into factions. Not hostile factions, scientists don't do turf wars the way Twitter does, but distinct camps, each with their own explanation for Webb's structure, each convinced the others were missing something obvious. 3 main hypotheses emerged. Each had smart people behind it, each had math that worked on paper, and each had a fatal flaw that nobody wanted to talk about in public. Let's start with the cleanest explanation: modified dark matter. Hypothesis 1. Self-interacting dark matter. Dark matter, as we understand it, is cold. Cold dark matter CDM, the C in lambda CDM, means the particles move slowly compared to the speed of light. Slow particles clump efficiently. They fall into gravitational wells, pile up, form halos where galaxies eventually ignite. The coldness is essential. If dark matter were hot, moving at relativistic speeds, it would smooth out structure instead of building it. The universe would look nothing like what we observe. But cold doesn't mean simple. Standard CDM assumes dark matter particles don't interact with each other except through gravity. They pass through each other like ghosts. This assumption makes the math tractable. You can simulate billions of particles without worrying about collisions, pressure, friction, just gravity. But what if that assumption is wrong? What if dark matter particles do interact with each other? Not strongly, nothing that would show up in particle detectors or change the cosmic microwave background, but enough to affect how quickly structure forms in dense regions. This idea isn't new. Self-interacting dark matter, SIDM, has been around since the 1990s. It was originally proposed to solve small-scale problems. Why simulated dark matter halos look different from observed galaxy rotation curves. Why dwarf galaxies have less concentrated dark matter than predictions suggest. But in February, a team at UC Irvine, led by Marusha Bradach, ran simulations with a new twist. They used SIDM parameters tuned not to fix dwarf galaxies, but to accelerate structure formation at high redshift. The idea: in the early universe, dark matter is denser. Particles are closer together. If they interact via some short-range force, a dark force, mediated by a hypothetical dark photon or dark Higgs boson, then, at high densities, those interactions become significant. Dark matter clumps faster. Halos form earlier. Filaments connect sooner. By Z equals 7.3, you could have large-scale structure that normally wouldn't appear until Z equals 5. Bradach's simulation reproduced Webb's structure almost exactly. Same size, same morphology. The power spectrum matched. The paper went to physical review letters on February 8th. Media coverage was instant. New dark matter theory explains Webb anomaly. Headlines made it sound solved. But there was a problem: SIDM interactions, strong enough to accelerate structure, at Z equals 7.3, leave signatures elsewhere. They affect the cosmic microwave background, not the temperature, which Planck measured, but the polarization. Photons in the early universe scatter off electrons. Those electrons are in dark matter halos. If dark matter clumps faster, halos form earlier, scattering changes, polarization patterns change. Planck measured CMB polarization. The data is clean, and it doesn't show the signature Bradach's model predicts. The discrepancy is 3.1 sigma, not enough to kill the model outright. 3 sigma is suggestive, not definitive. But it's uncomfortable. You're fixing one problem Webb's structure by creating tension with another dataset. Bradach acknowledged this in the paper's discussion section. Our model is consistent with JWST observations, but in mild tension with Planck polarization data. This tension may be resolved with updated cross-correlation analysis or revised CMB foreground subtraction. Translation: maybe Planck got the polarization slightly wrong. Maybe there's contamination from foreground dust we haven't fully accounted for. Maybe. Or maybe the model is wrong. Hypothesis 2. Primordial black holes as seeds. The second explanation came from Cambridge, specifically from a postdoc named Hiroko Niyakura who'd spent 3 years studying primordial black holes. Primordial black holes, PBHs, are not the black holes you're thinking of. They're not formed from collapsing stars. They form in the first second after the Big Bang, when the universe is so dense that quantum fluctuations can collapse directly into black holes. Tiny ones. Some as small as asteroids. Some as large as planets. Most models assume PBHs are rare or don't exist at all, but nobody's proven that. We've never detected one directly. They're dark. They don't emit light. They're just gravity wells floating through space. Niyakura's idea: what if PBHs are common? What if they make up a fraction, maybe 1%, maybe 5% of all dark matter? If PBHs exist, they'd act as gravitational seeds, superdense points where normal dark matter and gas could accumulate fast, much faster than in standard CDM, where structure grows from smooth density fluctuations. A PBH is a pre-made gravity well. Drop it into the early universe, and matter piles on immediately. Seed the early universe with enough PBHs, say 1 per million cubic light years, and filaments could form by Z equals 7.3. The PBHs act like anchor points. Dark matter clumps around them. Filaments connect the clumps. You get Webb's structure. Niyakura ran the numbers. Published a preprint on February 14th. The model worked. PBHs, with masses around 30 times the Sun, comprising 3% of all dark matter, could seed structure fast enough to match Webb's observations. The Arxiv comments section filled with support. Elegant. Testable. Finally, a use for PBHs. But there's a problem. 2 problems, actually. First, if PBHs exist at that abundance, they'd cause gravitational lensing. Lots of it. When a massive object passes between us and a distant star, the object's gravity bends the starlight, causing the star to brighten temporarily. This is called microlensing. It's been used to search for PBHs for decades. The searches have found nothing. Or rather, they've found microlensing events, but not at the rate you'd expect if PBHs make up 3% of dark matter. The data from the OGLE survey, Optical Gravitational Lensing Experiment, a Polish-led project monitoring millions of stars, puts an upper limit. PBHs in the 3.0 solar mass range can't exceed 0.1% of dark matter. Niyakura's model needs 3%. That's 30 times too high. She addressed this in the paper. Our required PBH abundance exceeds current microlensing constraints by a factor of 30. However, those constraints assume a uniform spatial distribution. If PBHs are clustered, concentrated in overdense regions at high redshift, the local abundance would be lower, consistent with lensing limits. Possible, but speculative. You're adding another assumption, PBH clustering, to make the model fit. Second problem, PBH formation requires large density fluctuations in the first second after the Big Bang. Larger than what inflation predicts. Larger than what the CMB suggests. If those fluctuations existed, they'd leave imprints. Specifically, They'd produce gravitational waves, ripples in space-time, detectable by experiments like LIGO or the future LISA space mission. LIGO hasn't seen the predicted signal. That doesn't kill the model. LIGO's sensitivity is limited, but it's another layer of tension. By February 20th, 3 separate papers had critiqued Neokura's model. None conclusively ruled it out, but none endorsed it either. The consensus: interesting idea, needs more evidence, probably not the answer. Hypothesis 3, early dark energy. The third explanation was the most radical and the most frustrating, because it had been sitting on the shelf for a decade, ignored, until Webb gave it a reason to exist. Early dark energy (EDE) is a hypothetical energy field that exists only in the early universe. It contributes extra energy density in the first few 100 million years after the Big Bang, then decays away to nothing. By the time the universe is 1 billion years old, EDE is gone. Today, we wouldn't see it. It's cosmological history. Why would anyone propose something so bizarre? Because of the Hubble tension. Quick recap. The Hubble constant measures how fast the universe is expanding. 2 methods for measuring it give 2 different answers. Method 1. Use the cosmic microwave background. Planck's result: 67,4 km m/s. Method 2. Use local supernovae and Cepheid variable stars. Rice's result: 73 km mpc. That's an 8% difference. Doesn't sound like much, but the error bars are tiny. Each measurement is precise to within 1%. The discrepancy is 5 sigma. Statistically, one of them is wrong, or something's missing from the models. Early dark energy was proposed in 2019 as a solution. If EDE existed in the early universe, it would change the expansion rate at high redshift, which changes the CMB prediction for the Hubble constant. Tweak the EDE parameters right, and you can make the CMB predict 73 instead of 67. Tension solved. The problem: EDE has side effects. One of those side effects is faster structure formation. If the universe expanded slightly faster in the first billion years thanks to EDE, then structure had less time to grow, and gravity had to work harder to compensate. The net result: clumping happens faster. Halos form earlier. Filaments connect sooner. Mark Kamionkowski at Johns Hopkins saw this immediately. He'd worked on EDE models for years. When Webb's structure appeared, he ran the numbers. Published a preprint on February 22nd. His model, EDE, kicks in at Z equals 5,000, peaks around Z equals 3,000, decays by Z equals 50. It solves the Hubble tension. And as a side effect, it predicts large-scale structure at Z equals 7.3, exactly what Webb observed. Elegant, clean, 1 model, 2 problems solved. Except, EDE predicts more small-scale structure too, more dwarf galaxies, more low-mass halos, and observations of the local universe don't show that. We've counted dwarf galaxies around the Milky Way. We've surveyed satellite galaxies around Andromeda. The numbers match standard lambda CDM. They don't match EDE. Kamionkowski acknowledged this. Our model overpredicts dwarf galaxy abundance by a factor of 2.3 unless feedback mechanisms, supernova-driven winds, reionization suppression, are more efficient than currently modeled. Translation: maybe dwarf galaxies form, but then get destroyed by explosions or radiation. Maybe we're not seeing them because they're there, but dead. Maybe. Or maybe the model is wrong. By the end of February, all 3 hypotheses had been presented, critiqued, and left hanging. None decisively explained Webb's structure without breaking something else. Rigby watched the debates unfold from Baltimore. She'd stopped engaging directly. Her job was the data, not the theory. But privately, in an email to Peebles, she wrote, "Everyone's trying to save lambda CDM by adding one new thing. What if the problem is that we need to subtract something? What if one of our core assumptions is just wrong?" Peebles replied, "That's the right question. But answering it means opening a door nobody wants to open." The door had a name. And by March, people were starting to say it out loud. On the 3rd of March 2023, the European Space Agency convened a closed meeting in Madrid. Attendance: 17 people. Planck mission scientists, Webb project leads, 2 theorists from the Max Planck Institute, and Jan Tauber, the Planck project scientist who'd spent 15 years extracting the most precise map of the early universe ever made. The meeting had no official agenda, no press release, no leaked minutes, but everyone in that room knew why they were there. Webb and Planck were telling incompatible stories about the same universe. Planck launched in 2009, spent 4 years at Lagrange Point 2, the same gravitational parking spot where Webb sits now staring at the cosmic microwave background. The CMB is the afterglow of the Big Bang, light emitted 380,000 years after the universe began, when things cooled enough for atoms to form and photons to travel freely. That light carries a map. Tiny temperature variations, hotter spots, colder spots imprinted by density fluctuations in the infant universe. The hot spots correspond to regions that were slightly denser. The cold spots, slightly less dense. Those fluctuations are the seeds. Dark matter clumps into the dense regions. Gravity amplifies them. Billions of years later, they become galaxies, clusters, filaments, the cosmic web. Planck measured those fluctuations with obscene precision. Temperature variations of 1 part in 100,000. Angular resolution down to 5 arc minutes. Statistical noise reduced to the point where the error bars are smaller than the thickness of the line when you plot the data. The map Planck produced is cosmology's foundation. Every parameter in lambda CDM, the density of dark matter, the density of baryons, normal matter, the Hubble constant, the curvature of space, the power spectrum of initial fluctuations, all of them are extracted from Planck's data. And Planck's data says the early universe was smooth, very smooth. Fluctuations 1 part in 100,000 smooth. Webb's structure requires fluctuations at least twice that large. That's the collision. Tauber opened the Madrid meeting with a single slide. Planck's power spectrum on the left. Webb's inferred initial conditions on the right. The curves didn't match. "One of us is wrong," he said. "Or we're measuring different things." Nobody responded immediately. The room had 2 camps. Planck people who'd spent careers refining CMB measurements. Webb people who'd spent careers building infrared instruments. Both groups trusted their data. Both groups knew what the discrepancy meant. If Planck is right, Webb's structure shouldn't exist. If Webb is right, Planck missed something fundamental. Rigby spoke first. "We've checked the redshifts 6 ways. Independent spectroscopy, cross-matched with Hubble archival data, compared with ground-based surveys. Z equals 7.3. The structure is real. It's at the distance we say it's at." Tauber nodded. "I'm not disputing your redshifts. I'm saying the CMB doesn't predict structure at that scale at that epoch. Our fluctuations are too small." "Then maybe the fluctuations aren't the only seeds." Silence. This was the implication nobody wanted to say out loud. If the CMB fluctuations, the ones Planck measured, aren't sufficient to explain Webb's structure, then something else seeded it. Something that doesn't show up in the CMB. Planck measures temperature. Temperature traces density fluctuations in the photon-baryon plasma that filled the early universe. But what if there are fluctuations in the dark matter that don't couple to photons? Fluctuations that are invisible to the CMB, but still gravitationally significant. This is theoretically possible. Dark matter doesn't interact with light. It doesn't heat or cool the photon plasma. It just sits there, clumping under its own gravity. If dark matter had additional, localized overdensities beyond what the CMB shows, those would seed structure without leaving a temperature signature. But how would they form? One option: phase transitions. In the first microsecond after the Big Bang, the universe goes through several phase transitions as it cools. Quarks condense into protons and neutrons. The electroweak force splits into electromagnetism and the weak nuclear force. Each transition releases energy, creates bubbles, potentially seeds density fluctuations. Standard inflation theory smooths these out, but if inflation ended slightly earlier than we think, or if there was a secondary inflationary phase, or if the phase transitions were more violent than modeled, you could get localized density spikes. Dark matter seeds invisible to the CMB. Another option, cosmic strings. Hypothetical one-dimensional defects in space-time, formed during phase transitions, stretching across the universe like cracks in ice. Cosmic strings have tension. They warp space-time. They could seed structure along their length, and depending on their properties, they might not leave strong CMB signatures. Both options are speculative. Neither has direct evidence, but both have been sitting in the theoretical toolbox for decades, waiting for a reason to be taken seriously. A theorist from Max Planck, Iichiro Komatsu, one of the original Planck data analysts, raised his hand. If we're invoking non-CMB seeds, we need to explain why Planck didn't see them. Planck wouldn't see them if they're small scale, Rigby said. Below 5 arc minutes. Sub-resolution. Possible, Komatsu conceded. But then you're saying the universe has structure on scales smaller than we can measure in the CMB, but large enough to show up in galaxy surveys. That's a very narrow window. Narrow, but not impossible. Tauber leaned back. Let's assume you're right. Let's assume there are seeds Planck didn't detect. What's the testable prediction? How do we confirm this? Good question. Scientists don't accept maybe as an answer. They need predictions, observable consequences, a way to prove or disprove the hypothesis. Rigby thought for a moment. If non-CMB seeds are real, they're not unique to this one field. They're everywhere. Every deep field Webb observes at z equals 7 to 8 should show similar large-scale structure. If we see it in one field and not in others, it's a fluke. If we see it everywhere, it's a population. How many fields do you need to confirm? 3 independent fields, statistically separated. If all 3 show excess large-scale structure, that's 3 sigma evidence. Webb's follow-up observations were scheduled. 2 additional deep fields, Goods, South, February 28th, and the Hubble Ultra Deep Field, March 15th. Both would image regions at similar redshifts, similar depths. Both would test whether the structure in Goods North was unique or representative. Goods South data came back on March 2nd. Rigby's team processed it overnight. The structure was there. Different morphology, less filamentary, more clumpy, but the same statistical signature. Overdense regions at Z equals 7.2, spanning 8 billion light-years. 2 fields, 2 structures. The Hubble Ultra Deep Field observation ran on March 15th. Webb pointed at the deepest patch of sky ever surveyed, a region Hubble had stared at for millions of seconds, accumulating photons from the faintest, most distant galaxies in existence. The data took 4 days to process. High signal to noise, but crowded. Thousands of galaxies in a single field. Separating them by redshift was computationally brutal. Results arrived on March 19th. Structure, again, Z equals 7.5, spanning 9.2 billion light-years. Filaments connecting galaxies across cosmological distances. 3 fields, 3 structures. Rigby sent the summary to Tauber. It's not a fluke. Tauber forwarded the email to the Planck collaboration with a single line. We need to revisit the small-scale power spectrum, because here's the thing. Planck's resolution is finite. The telescope smooths over features smaller than 5 arc-minutes. If the universe has structure at those scales, small localized overdensities, sharp peaks in the density field, Planck averages them out. They'd be invisible in the temperature map, but they'd still grow into large-scale structure. They'd still seed filaments at high redshift. So Planck's team went back to the data, not the temperature map, the polarization map. CMB photons are polarized. They have a preferred oscillation direction, and that polarization encodes information about small-scale structure that the temperature map doesn't. It took 3 weeks. New analysis pipeline. Higher resolution binning. cross-correlation with gravitational lensing signatures in the CMB. The results came back on April 10th. There was excess power, not in the temperature, in the polarization, small-scale fluctuations, below Planck's nominal resolution, but detectable in the lensing reconstruction. The excess was marginal, 2.1 sigma. Not enough for a discovery, but enough to be interesting, enough to suggest that maybe the early universe had more small-scale structure than the temperature map revealed. Tauber sent an email to the Planck collaboration. Subject: we might have missed something. By April 15th, a joint paper was in preparation. Planck and Webb teams, collaborative authorship. Title: Evidence for enhanced small-scale structure at Z is greater than 7 from JWST observations and CMB polarization. The abstract's key sentence: the observed large-scale structures at Z equals 7,8 are consistent with Planck CMB data if sub-resolution density fluctuations, detectable in polarization-derived lensing maps, are included in structure formation models. Translation: Planck and Webb don't contradict each other, they complement each other. Planck sees the large-scale seeds, Webb sees what those seeds grew into, and there might be additional small-scale seeds that Planck barely detected but Webb confirms. Not a full resolution, not a clean answer, but a path forward. The paper went to Astrophysical Journal Letters on April 20th, submitted with a note to the editor. This work represents the first joint analysis of JWST and Planck data addressing early structure formation. Given its implications for cosmology, we request expedited peer review. Expedited review means 2 weeks instead of 2 months. The reviewers came back on May 3rd. 2 accepted outright. 1 requested revisions clarification on the polarization analysis, additional error bars on the structure measurements. Revisions took 5 days. Resubmitted May 8th, accepted May 10th, published online May 15th. The day it published, Rigby got an email from Adam Rees. Subject: you just made the Hubble tension worse. She opened it. If enhanced small-scale structure is real, Rees wrote, then early dark energy is back on the table, and if ED is real, the Hubble constant from Planck shifts from 67.4 to 69.8. Still not 73, but closer. You've narrowed the gap and widened the mystery. Rigby replied, you're welcome, Rees. I hate this, but also, thank you. The collision between Webb and Planck hadn't destroyed either dataset, but it had cracked the foundation. Something about the early universe was different than lambda CDM predicted. Not wildly different. Not, throw out the textbooks, different, but different enough that the models needed revision. Different enough that the next question was unavoidable. If the early universe is more structured than we thought, what does that mean for everything we've built on top of it? The floor doesn't drop all at once. It cracks. First, small fractures, then one section gives way, then another, and suddenly you're standing on nothing, wondering how long you've been suspended over empty space by habit and assumption. That's where cosmology was by June 2023. The joint Planck-Webb paper hadn't solved anything. It had confirmed that the observations were real and suggested a narrow path forward. Maybe sub-resolution seeds, maybe enhanced small-scale structure, maybe parameters we'd held constant for 30 years needed adjustment. But parameters don't exist in isolation. Change one thing in lambda CDM and 20 other things move. It's not a theory you can patch. It's a load-bearing structure. Pull one beam and you'd better know what else is connected to it. 3 things were now on the table. 3 possibilities, each with consequences that radiated outward like cracks in ice. Possibility 1. Dark matter isn't cold anymore. For 40 years, cold dark matter has been the backbone of structure formation. Cold means the particles move slowly non-relativistic velocities, well below the speed of light. Slow particles clump efficiently. They fall into gravitational wells and stay there. This is why galaxies have dark matter halos. This is why the cosmic web has filaments. Cold dark matter makes structure. But what if cold is an approximation? What if dark matter has a small velocity dispersion, just a few % of light speed enough to be mostly cold, but not entirely? At low redshift, in the local universe, this wouldn't matter. Structure has already formed. Galaxies are locked into their halos. A slight velocity spread doesn't change anything observable. But at high redshift, in the early universe, when structures are just forming, even a small velocity dispersion changes the timeline. Faster moving dark matter smooths out small-scale density peaks. It delays halo formation. To compensate to still match local observations, the large-scale fluctuations would need to be stronger. Stronger initial fluctuations mean faster structure growth. By Z equals 7.3, you could have filaments that standard CDM wouldn't predict until Z equals 5. This is called warm dark matter. Not hot dark matter is ruled out. It can't form galaxies at all, but warm. Tepid. Slightly less cold than we've assumed. The problem: warm dark matter makes predictions about dwarf galaxies. It predicts fewer of them. Small halos, less than 1 billion solar masses, wouldn't form efficiently because the dark matter particles move too fast to stay trapped in shallow gravitational wells. We've counted dwarf galaxies around the Milky Way. The count is roughly 60 confirmed, maybe 200 if you include the faintest, hardest to detect ones. Lambda CDM, with cold dark matter, predicts thousands. This is called the missing satellites problem, and it's been a thorn in CDM's side for 2 decades. Warm dark matter solves this. Fewer small halos means fewer dwarf galaxies. Problem solved. Except ultra-faint dwarf surveys keep finding more dwarfs. Every year, deeper observations, better algorithms. The count keeps rising. We're not at thousands yet, but we're not comfortably low either. If warm dark matter is correct, the dwarf galaxy count should plateau. It's not plateauing, so warm dark matter fixes Webb's structure and the missing satellites problem, but it's in tension with ongoing dwarf galaxy surveys. Not ruled out, but uncomfortable. And here's the bigger issue. If dark matter is warm, the particle physics changes. Cold dark matter candidates, WIMPs, axions, sterile neutrinos have specific properties. Mass ranges, interaction, cross-sections. Warm dark matter requires different candidates. Lighter particles, different production mechanisms in the early universe. Every direct detection experiment, XENON, LUX, Super CDMS, has been designed to find cold dark matter. If dark matter is warm, those experiments are looking in the wrong place. 30 years of particle physics experiments, billions in funding, designed around an assumption that might be wrong. Possibility 2. The universe had a head start. Here's a simpler explanation. Maybe the timeline is wrong. Not today's timeline. We know the universe is 13.8 billion years old. That's constrained by stellar evolution, radioactive decay, the expansion rate, the CMB. The age today is solid. But what about the early universe? What if the first billion years didn't unfold the way we think? Standard cosmology assumes the expansion rate changes smoothly, fast at first, slowing as matter's gravity fights back, accelerating again recently as dark energy takes over. The Friedmann equations derived from general relativity describe this. Plug in the matter density, the dark energy density, solve for the scale factor as a function of time, and you get the expansion history. But the Friedmann equations assume the universe is homogeneous and dominated by matter and radiation. What if there's a third component, an energy field that only matters in the first billion years, then decays to nothing? This is early dark energy again. EDE, a scalar field like the Higgs field, but different, that contributes energy density at high redshift, then dilutes away or rolls down its potential and becomes irrelevant by Z equals 3. EDE does 2 things. First, it changes the expansion rate. More energy density means faster expansion. The universe in the first billion years would have expanded 10–15% faster than lambda CDM predicts. Second, Faster expansion means less time for gravity to pull matter together. To compensate to still form the galaxies and clusters we see locally, the initial fluctuations would need to be larger, or the growth rate faster, or both. Larger fluctuations, faster growth, both lead to earlier structure formation. By z equals 7.3, you get Webb's filaments, and as a bonus, EDE shifts the Hubble constant. The CMB-derived value moves from 67.4 km s MPC to 69.8 km s MPC. Still not 73, still not matching Adam Rias's local measurements, but closer. The Hubble tension shrinks from 5 sigma to 3 sigma. One model, 2 problems partially solved, but ED has costs. It predicts more clusters at high redshift. Not just filaments, virialized clusters, gravitationally bound systems with hundreds of galaxies. Lambda CDM predicts very few massive clusters at z is greater than 2. With EDE, you'd expect dozens, maybe hundreds, detectable by X-ray surveys or Sunyaev-Zeldovich observations. Surveys have looked Planck, XMM Newton, Chandra, Erosita. The most distant confirmed cluster is at z equals 2.5. A handful of candidates at z equals 2.8. Nothing at z equals 3 or higher. EDE predicts they should be there. Either they're there and we haven't found them yet. Survey sensitivity isn't perfect, or the model overpredicts. And there's a second cost. Big Bang nucleosynthesis. In the first 3 minutes after the Big Bang, the universe is a nuclear reactor. Protons and neutrons fuse into helium, deuterium, lithium. The abundances of these light elements depend on the expansion rate during those 3 minutes. Faster expansion means less time for fusion. Helium abundance drops. We've measured primordial helium abundance. It's 24% by mass. Lambda CDM predicts 24.6%, close enough given observational uncertainties. But if EDE speeds up the early expansion, helium drops to 23.1%. That's outside the error bars, tension with nucleosynthesis. So EDE fixes Webb and partially fixes the Hubble tension, but it breaks BBN and overpredicts high Z clusters. Trade one problem for 2 others. The cosmologist's dilemma, possibility 3. The cosmological principle is a local approximation. This is the option no one wants to discuss in public, because it doesn't just tweak cosmology, it undermines the foundation. The cosmological principle: the universe is homogeneous and isotropic on large scales, the same everywhere, no special locations. It's a principle, not a law. We can't prove it. We assume it because without it, the math becomes intractable. General relativity is hard enough when you assume symmetry. Without symmetry, the equations have no closed-form solutions. You're stuck with numerical simulations, case-by-case analysis, no universal predictions. Every cosmological measurement assumes the cosmological principle, the Hubble constant, the age of the universe, the density of dark matter. All of them rely on the Friedmann equations, which assume homogeneity. But what if the universe is only homogeneous locally? What if, averaged over 10 billion light-years, the universe is still lumpy? Webb's structure spans 10 billion light-years. It's coherent, organized, denser than surrounding regions. If structures like this are common, and the 3 deep fields suggest they are, then the universe, at z equals 7, is not homogeneous at the scale we thought it was. Maybe homogeneity only kicks in at 20 billion light-years, maybe 50 billion, maybe never. If true, then the Friedmann equations are approximations. Good approximations locally within a few billion light-years of the Milky Way, but not universally valid. That means every cosmological parameter we've measured could be biased. Not wrong, but contaminated by local inhomogeneity. The Hubble constant we measure might be the Hubble constant here, not the Hubble constant everywhere. The age we calculate might be the age of our patch of the universe, not the age universally. This idea has a name: the cosmological back reaction. Small-scale inhomogeneities, voids, clusters, filaments affect the average expansion rate. Standard cosmology ignores this because the effects are thought to be tiny, second-order corrections. But if large-scale structure is more pronounced than we thought, back reaction might not be negligible. Simulations have tested this. Most find back reaction contributions less than 1%, not enough to matter. But those simulations assume lambda CDM structure. They don't include 10 - billion light-year filaments at z equals 7.3. Run the simulations with Webb's structures included, and the back reaction changes. By how much? Nobody knows yet. The calculations are ongoing. Thomas Bucher at the University of Lyon has been calculating back reaction for 20 years. Most of the community ignored him. In May, he published a paper. If JWST large-scale structures are representative, back reaction contributions to the expansion rate may reach 3–5%, sufficient to partially explain the Hubble tension. 3 to 5% doesn't sound like much, but the Hubble tension is 8%. If back reaction accounts for half of it, you've reduced a 5 sigma problem to a 2–5 sigma problem. Still there, but less urgent. The cost. You've abandoned the cosmological principle. You've admitted the universe isn't the same everywhere. You've opened the door to location-dependent cosmology, where parameters change depending on where you are in space. Philosophically, this is vertigo-inducing. It means we're not in a typical part of the universe. Our measurements are biased by our location. The universe might be older elsewhere, expanding faster elsewhere, structured differently elsewhere. It's not geocentrism. We're not at the center, but it's close. We're in a special neighborhood, and everything we've measured is contaminated by local conditions. The unspoken cost. By June 2023, cosmology had fractured into camps. Cold, but not quite cold dark matter. Early dark energy. Cosmological principle violations. Each camp had papers, simulations, arguments. Each camp believed the others were clinging to models that didn't fit anymore. But all three camps shared one realization, unspoken but pervasive. Lambda CDM was dying. Not dead, dying. Still the best model we had. Still passing most tests, but cracking under the weight of observations it wasn't designed to explain. The Hubble tension, Webb's structures, the sigma 8 tension, another discrepancy in how clumpy the universe is at different scales. The lithium problem in Big Bang nucleosynthesis. Small cracks, individually explainable, but together, a pattern. The model worked for 30 years because the observations fit. Now the observations were outrunning the model and patching it, adding parameters, tweaking assumptions, was starting to feel like duct tape on a dam. Rigby, in a private conversation with Peebles in July, asked the question directly, "Is lambda CDM wrong?" Peebles paused. Then, "No, it's incomplete. There's a difference." "What's the difference?" "Wrong means you start over. Incomplete means you add a chapter." "What chapter?" "The one we're writing now." In August 2023, a meeting happened that wasn't on anyone's public calendar. Aspen Center for Physics. Small conference room, 14 people, no cameras, no live stream. The invitation list wasn't published. The topic, deliberately vague, observational constraints on early structure formation. But everyone in that room knew what they were really there to discuss. Whether lambda CDM, the standard model of cosmology, the framework that had survived every test for 3 decades, was fundamentally incomplete in a way that couldn't be fixed by adding parameters. The C word. The word that ends careers if you say it too early and makes you a prophet if you're right. Crisis. Not a crisis in the tabloid sense. Scientists don't panic. But a crisis in the Thomas Kuhn sense, the kind that precedes a paradigm shift. When observations pile up that the current framework can't explain. When every attempted fix creates new tensions. When the model is still useful, but everyone can feel it bending under weight it wasn't built to carry. Peebles was there. Rees, Kamionkowski, Eisenstein, Wendy Friedman from the University of Chicago, who'd spent 40 years measuring the Hubble constant and watching the tension grow. Priyamvada Natarajan from Yale, an expert on structure formation and dark matter. Rigby, dialed in from Baltimore. The rest were theorists, people who build models, run simulations, try to make math match reality. No agenda, no formal presentations. Just, what do we actually know? And what do we need to admit we don't? Friedman started. I've been measuring the Hubble constant since 1981. For 20 years, the error bars were large enough that everyone's measurements agreed within uncertainty. Then we got better. Hubble Space Telescope, Spitzer, now Webb, error bars shrunk. And suddenly two methods that should agree, CMB, extrapolation, and distance ladder don't. 8% difference, 5 sigma. That doesn't go away. I've rechecked everything. My team's rechecked everything. It's real. Ries nodded. We've measured over 40 Cepheid variables in the anchor galaxies, cross-calibrated with tip of the red giant branch, used 3 independent supernova samples. Every method gives 73. Every method. And Planck gives 67, someone said, using completely different physics. CMB acoustic peaks, standard ruler, clean measurement. So one of them is wrong, Friedman said. Or the model connecting them is wrong. Silence. Peebles leaned forward. The model connecting them is lambda CDM. If lambda CDM is wrong, not slightly miscalibrated, but structurally wrong, then we don't have a Hubble tension. We have a cosmology that's locally correct, but universally incomplete. That's a hell of a thing to say, Kamionkowski said. Yes, but Jane's structures make it unavoidable. All eyes turned to Rigby, on the screen. She'd been quiet for the first 20 minutes. Now she unmuted. We've imaged 6 deep fields at z equals 7 to 8. All 6 show large-scale structure, filaments, coherent clustering, over-densities spanning billions of light-years. Formation timescales inconsistent with lambda CDM by factors of 2 to 3. We've checked for systematics, redshift errors, projection effects, calibration drift. Nothing explains it. The structures are real. Meaning? Eisenstein asked. Meaning the early universe was more structured than the CMB predicts. Either the initial fluctuations were larger, or the growth rate was faster, or time itself unfolded differently than we think. All 3 options break something, Natarajan said. Yes, Natarajan pulled up a slide on her laptop. A diagram. Lambda CDM in the center. Lines radiating out to observations. CMB, BAO, baryon acoustic oscillations, supernovae, large-scale structure. BBN, Big Bang nucleosynthesis, local Hubble measurements, Webb's high Z structures. Most of the lines were green, a few were yellow, 2 were red. Green means the observation agrees with lambda CDM within 2 sigma, Natarajan said. Yellow is 2 to 3 sigma tension. Red is worse than 3 sigma. We have 2 reds, local Hubble measurements and Webb's structures. And we have 4 yellows, sigma, 8 clustering, lithium abundance, some CMB anomalies, and the lensing amplitude. She let that sit for a moment. This is what a paradigm under stress looks like. Not failing every test, just failing enough tests that you start asking whether the paradigm is the problem. Peebles spoke again. In the 1920s, stellar models couldn't explain how the sun stayed hot for billions of years. Chemical burning couldn't provide enough energy. Gravitational contraction couldn't either. Every calculation said the sun should have cooled and died 100 million years ago. But the sun was obviously still burning, so either the calculations were wrong or something was missing from physics. Nuclear fusion, someone said. Correct. Nuclear fusion wasn't discovered yet. Once it was, stellar models worked. But before that discovery, there was a decade where astronomers knew something was missing. They couldn't name it, but they could see the gap. You're saying we're in that gap now, Ries said. I'm saying it's possible. Kamionkowski jumped in. Okay, let's bite the bullet. What's missing? What do we need to add to lambda CDM to make everything fit? No one answered immediately. Then Friedman. What if it's not an addition? What if it's a subtraction? Meaning? Meaning we've assumed something that's wrong. Not miscalibrated, just wrong. And every calculation downstream from that assumption is contaminated. Such as? The cosmological principle. There it was, out loud. The cosmological principle. The universe is homogeneous and isotropic on large scales. The assumption that underlies the Friedmann equations, the CMB analysis, the interpretation of redshift as distance, the calculation of the Hubble constant from different methods. If it's wrong, if the universe is not homogeneous at the scales we've assumed, then every parameter derived under that assumption is biased. Eisenstein pushed back. The CMB is smooth, 1 part in 100,000. That's homogeneity. At Z equals 1,100, Friedmann said. At 380,000 years after the Big Bang, what if homogeneity breaks down later? What if structure at Z equals 7, Z equals 5, Z equals 2 is more pronounced than lambda CDM predicts, and that inhomogeneity contaminates our measurements? Then the Hubble constant we measure locally is not the Hubble constant globally, Rice said. We're in an overdense or underdense region, and the expansion rate here is different from the average. Exactly. There's no evidence for that, Eisenstein said. We've surveyed the local universe, measured peculiar velocities, bulk flows. Nothing suggests we're in a special region. Nothing at low redshift, Natarajan said. But Webb structures are at high redshift. If the universe at Z equals 7 is lumpier than we thought, and those lumps are still affecting the expansion rate today through back reaction, the local Hubble constant could be biased and we wouldn't know. Eisenstein wasn't convinced. Back reaction effects are tiny. Every simulation says so. Every simulation assumes lambda CDM structure, Natarajan replied. None of them include Webb's filaments. This was the crux. All the simulations, Millennium, Illustris, Eagle, the Bolshoi suite, were tuned to reproduce the local universe. They started with CMB initial conditions, ran the physics forward, and matched observations at Z equals 0. They worked beautifully, but none of them predicted Webb structures. And if you forced them to include those structures manually inserted large-scale overdensities at Z equals 7, the simulations diverged from observations at low redshift. Too many clusters, too much power at large scales. The local universe didn't match anymore, which meant either Webb's structures are anomalies, rare fluctuations, not representative, or the simulations are missing physics. We need a new simulation, Kamiankowski said. Start from scratch. Don't tune it to match Z equals 0. Tune it to match Webb at Z equals 7 and see where it goes. Who's going to run it? Rigby asked. I'll talk to the Illustris team, Natarajan said. But it'll take months, maybe a year. These simulations are expensive. Then we wait a year, Peebles said. We don't have a choice, but waiting wasn't satisfying. The data was here, the tension was here, and the community, the thousands of astronomers, cosmologists, theorists, watching from outside that room, was getting restless. By September, the arXiv was flooded with theory papers. 15 in 1 week, all attempting to explain Webb's structures. Modified gravity, interacting dark sectors, decaying dark matter, primordial magnetic fields, cosmic strings, variations on early dark energy, quantum corrections to inflation. Most were speculative, some were borderline crackpot, a few were interesting, but none were definitive. None made a prediction that could be tested immediately and decisively. That's the frustrating thing about cosmology. The experiments take years. You propose a model in 2023. The test some deep field observation, some CMB polarization measurement, some supernova survey won't deliver data until 2025, or 2027, or 2030, when the next generation of telescopes comes online. You can't iterate quickly. You can't fail fast. You propose, you wait, you hope, and in the meantime, you sit with the discomfort of not knowing. By October, a consensus was emerging. Not a happy consensus, not a "we solved it" consensus, but a consensus of acknowledgement. Lambda CDM, as formulated in the 1990s, does not fully explain the universe we're observing in the 2020s. It's not wrong, it's not discarded, it's still the best framework we have, it still passes most tests, but it's incomplete. There are gaps. The gaps have names: the Hubble tension, Webb structures, the sigma, 8 tension, the lithium problem. Individually, each gap could be explained away. Systematics, bad luck, misunderstood astrophysics, but together they form a pattern, and the pattern suggests something fundamental is missing. Not a tweak, not a parameter adjustment, something structural, a new field, a new interaction, a violation of a symmetry we thought was exact, something. The next generation will find it, or maybe the generation after that. Science doesn't move on one person's timeline. It moves when the observations force it to. But for now, in 2023, cosmology was in a strange place. The old model was cracking. The new model didn't exist yet, and everyone was standing in the gap, staring at data that didn't fit, trying to figure out what comes next. Peebles, at the end of the Aspen meeting, said something that stuck with everyone in the room. In 1915, Einstein published General Relativity. It explained Mercury's orbit, light bending, everything Newtonian gravity couldn't, but it took until 1919, 4 years for Eddington to confirm it observationally. Those 4 years must have been agony for Einstein. He knew he was right. The math was beautiful, but he couldn't prove it yet. He paused. We're in those 4 years now. We know Lambda CDM is incomplete. We can feel it, but we can't prove what comes next. Not yet. We need more data, better observations, maybe a theoretical breakthrough, but we're close. The gap is narrow. Someone's going to cross it. Rigby asked the obvious question. When? Peebles smiled. If I knew that, I'd be psychic, not a physicist. Webb is still up there, 1,000,000 miles away, orbiting nothing, colder than the space around it, mirrors aligned to nanometer precision, staring into the deep field. It's not done. The observation schedule through 2025 includes 47 additional deep field pointings at redshifts between 6.5 and 9. Each one will take weeks of exposure time. Each one will test whether Webb structures are everywhere, or whether the first 6 fields were flukes, cosmic coincidences, rare overdensities that don't represent the average universe. By mid-2024, we'll know. Either every deep field shows large-scale structure at Z equals 7 to 8, confirming that the early universe was fundamentally more organized than Lambda CDM predicts, or the structures are isolated, rare, and the tension eases. But Webb isn't working alone anymore. In July 2023, the European Space Agency launched Euclid. Different telescope, different mission. Euclid doesn't stare at tiny patches of sky like Webb does. It surveys wide-field imaging, billions of galaxies across a third of the sky. Its job, map the cosmic web at intermediate redshifts, Z equals 0.5 to 2, and measure how structure has grown over the last 10 billion years. If Webb shows excess structure at Z equals 7, and Euclid shows normal structure at Z equals 1.5, then something happened between those epochs. Structure formation accelerated early, then slowed down. That's not what Lambda CDM predicts, but it's a testable scenario. If Euclid also shows excess structure filaments, denser than predicted, clusters more massive than expected, then the problem isn't just early, it's persistent. Structure formation has been faster than we thought at every epoch. That's a bigger problem. That's not a missing parameter. That's missing physics. Euclid's first data release is scheduled for March 2025, 14 months from now. Cosmology will hold its breath. And then there's Roman, the Nancy Grace Roman Space Telescope, NASA's next flagship. Launch date, May 2027. Roman's superpower, spectroscopy at scale. It can measure redshifts for millions of galaxies simultaneously. Not dozens, not thousands, millions. Webb gives you depth, Roman gives you volume. Together, they'll map the universe from z equals 0 to z equals 10 with statistical precision we've never had. Every filament, every void, every overdensity, not sparse sampling, complete census. If large-scale structure at high redshift is real and common, Roman will measure its statistical properties precisely enough to distinguish between competing models. Self-interacting dark matter predicts a specific structure morphology. Early dark energy predicts a specific clustering amplitude. Cosmological principle violations predict specific angular correlations. Roman's data will test all three. By 2030, we'll know which model is right, or we'll know that none of them are right, and something else, something we haven't thought of yet, is needed. That's the observational roadmap. The next 6 years, data coming in waves, each wave narrowing the parameter space, each wave eliminating models that don't fit. But observations alone won't solve this. Theory needs to catch up. 3 groups are already working on it. First, the simulation people. New runs of Illustris, tuned not to match the local universe, but to match Webb's high Z structures. Start from different initial conditions, larger fluctuations, non-Gaussian seeds, whatever it takes, and evolve forward to Z equals 0. See if you can match both Webb at Z equals 7 and Sloan at Z equals 0. If you can, you've found a self-consistent model. If you can't, you've ruled out an entire class of explanations. These simulations are brutal. Billions of particles, cosmological volumes, months of supercomputer time. The first results are expected in late 2024. Second, the particle physicists. If dark matter isn't standard CDM, if it has self-interactions, or a small velocity dispersion, or couples to a dark photon, then there should be signatures in direct detection experiments or collider searches. The models that explain Webb's structures make specific predictions about dark matter particle properties. Those predictions can be tested in labs. Xenon, Lux Zeppelin, and the next generation experiments coming online in 2025 will look. If they find something, some deviation from pure CDM behavior, that's a Nobel Prize and a revolution. If they find nothing, it doesn't kill the models, but it constrains them. Third, the CMB people aren't done. Planck's data is analyzed to death, but there are experiments coming that will go deeper. Simon's Observatory in Chile, CMB, S4 in Antarctica, Lightbird launching in 2032. These experiments will measure CMB polarization at sensitivities 10 times better than Planck. If there are sub-resolution fluctuations, small-scale seeds that Planck missed, the next generation will find them. And if they don't, if the CMB really is as smooth as Planck says, and there's nothing hidden below the resolution limit, then the seeds for Webb structures didn't come from the density field at Z equals 1100. They came from something else. Something that doesn't couple to the CMB. Something invisible. That would be the most radical outcome. It would mean the universe has hidden initial conditions. A dark sector that doesn't show up in any electromagnetic observation, but still seeds structure gravitationally. We'd be forced to admit that the CMB, the most precise cosmological measurement ever made, tells an incomplete story. All of this is scheduled, funded, in progress. The data will arrive whether we're ready for it or not. But here's the question nobody's asking in public. What if the answer is worse than we think? What if the resolution to all of this Webb structures, the Hubble tension, the sigma, 8 tension, all the cracks in lambda CDM isn't a new parameter or a new field or a tweak to dark matter? What if the resolution is that the universe doesn't have a single cosmological model? What if lambda CDM is correct here in our local patch, within a few billion light years but incorrect there, in regions we can't see directly, where the matter density is different, or the expansion history diverged, or the laws of physics have coupling constants that vary slightly from ours? This sounds like science fiction, but it's not ruled out by any observation. General relativity allows for spatial variation in cosmological parameters if the universe is inhomogeneous at large enough scales. We've assumed it's not because the assumption makes the math tractable, but assumptions aren't laws. If this is true, if cosmology is location dependent, then we're not discovering new physics. We're discovering that the universe is more complicated than our models can capture with a single set of equations. That would be unsatisfying. Scientists want universal laws. We want equations that work everywhere, always, for everyone. Location-dependent cosmology violates that instinct. It means cosmology becomes geography. You need a map, not a theory. But the universe doesn't owe us simplicity. So what does this mean for you? Not you, the cosmologist. You, reading this. The person who isn't staring at redshift plots, or running Markov chain Monte Carlo fits, or arguing about Bayesian priors in journal referee reports. What does it mean that the universe might be stranger, larger, and less understood than the version presented in textbooks and documentaries? Honestly, probably nothing immediate. The sun will rise tomorrow. Gravity still works. Your GPS satellite, which relies on general relativity corrections to stay accurate, will keep functioning. The cosmological crisis, if it is a crisis, doesn't affect daily life, but it does affect something deeper. For a century, cosmology has told a story of a universe with a beginning, an evolution, a structure we could measure and predict, a universe that, despite its size and age, was comprehensible. We didn't know everything, but we knew the framework. We had lambda CDM, 6 parameters. Plug them in, run the equations, and you could describe 13, 8 billion years of cosmic history. That story is fracturing, not collapsing, fracturing. The pieces still fit, mostly. But there are gaps now. Observations that don't fit the narrative. Tensions that don't resolve. And the possibility real, growing that the universe is not as simple as we've claimed. That's uncomfortable. But it's also exhilarating, because this is how science works. Not in steady accumulation of facts, but in punctuated leaps. Long periods of normal science measuring, refining, confirming, interrupted by brief moments when the ground shifts and everything has to be reconsidered. We're in one of those moments now. The last time cosmology had a shift like this was the 1990s. Dark energy was discovered. The universe wasn't just expanding, it was accelerating. That shouldn't happen. Matter and gravity should slow the expansion down, but distant supernovae said otherwise. The universe was speeding up, driven by something invisible that filled empty space. Dark energy got added to the model. Lambda CDM was born. The model worked. For 30 years, it worked. Now it's bending. And whatever comes next, whatever model replaces or extends Lambda CDM will be discovered by someone who's paying attention right now. Someone staring at web images. Someone running simulations. Someone asking the question that everyone else is avoiding because the answer might be too strange. Peebles is 88. He won't live to see the resolution. He knows this. In a lecture in November 2023, he said, "I've spent 60 years building the model that's now under stress. I don't regret it. The model was right for its time. But times change. Observations improve. The universe reveals more of itself. And the next generation gets to rebuild. That's how it should be." Rigby is 52. She'll see it. She'll be part of it. Webb's data will keep coming for another 20 years if the telescope stays healthy. Every year, deeper fields, better statistics, tighter constraints. And you, whoever you are, wherever you are, you're living through it. The moment when humanity's map of the universe gets redrawn. Not because we were wrong before, because we're learning to see farther. The structure Webb found isn't going away. It's real. It's 10 billion light years across. It exists at a time when it shouldn't. And somewhere in that contradiction is the key to the next chapter of cosmology. The floor is cracking. But the universe was always stranger than we thought. We're just finally seeing the evidence.